Right, so welcome to class, guys. We're going to continue with Lagrange multipliers, which is where I left off at the end of last class. So if you remember, Lagrange multipliers are a way to take a constrained optimization problem and turn it into an unconstrained one. And there are two reasons you might want to do this. One of them is that it can help with intuition. So the constraints might make it hard to interpret an optimization problem, and so instead you can turn it into an unconstrained one and see if that's easier to figure out what it means. And the other then is for an algorithm. So with by turning an unconstrained, a constrained problem into an unconstrained one, you then open up the set of algorithms that you can apply to it, and that can be good. And this is just a generally useful technique, but it leads in particular to a famous machine learning technique, the support vector machine, which we're probably going to get to next class. So let's dive in. You remember Newton's method, right? So you take your function that you're trying to optimize, you Taylor expand it, make a second order Taylor expansion, and set the derivative with respect to the increment delta x to be 0, and that gets you the Newton step, right? All right, so at the end of class last time, we were looking at how we might go about extending Newton's method to handle equality constraints. And so if you remember, right, so these contours were the function f we're trying to optimize. And if you look at the gradient of f, right, that's just going to be an arrow pointing normal to one of the contours. And then this surface here is p of x equal to 0. And so if you look at the gradient of p, that's going to be pointing normal to that surface, right? And the optima were just going to be the places like this one, where if you take the gradient of p there and the gradient of f there, right? And these could be different lengths, but they're supposed to be pointing in the same direction. So we had that the gradient of p at x is equal to lambda times the gradient of f at x. And the lambda there was called a Lagrange multiplier. And the idea was that it corrects for the things being different scales, right? They're in different, they're in the same direction, but different scales. And so you multiply one by some real number lambda, and you get the other, right? So any questions so far? All right, cool. So we're going to be doing this a lot today. So let's take a look then at how we would start to figure out when we had hit an optimum of the function subject to a constraint, right? So again, this is our optimization problem to minimize f of x subject to p of x is equal to 0. F is a function from Rd to R. P is from Rd now to Rk, right? So there could be k different equality constraints rather than just one. And we want to satisfy all of them at the same time. And we're going to define g to be the gradient of f. So it takes x, which is a d-dimensional vector, and it returns the gradient, which is another d-dimensional vector. Okay? And we're going to start by looking at a useful special case, right? So we're going to have ax equal to b instead of p of x equal to 0. So that's the same as setting p of x is equal to ax minus b, right? And so in this case, what we want to do is we want to define a set C, which is the set of all x's such that ax equal b, right? Oops, that should be not match my parentheses, otherwise my slides will get a syntax error when I try and compile them. So what do we want to do, right? So what we would like is to have the gradient of f be orthogonal to this constraint set C, right? Now what does that mean? Well, so in general, some vector z is orthogonal to the set C, right? If and only if z transpose times x minus y is equal to 0 for all x and y in C, right? So geometrically, we have our constraint set C here, right, we have a vector, so we have points x and y that are in the constraint set, and we have a vector z, right, which I'm just going to base the vector at x, and we have that z is orthogonal to c if and only if this vector is orthogonal to the vector between these 2 points, right? So x minus y is that vector, right? And these are going to be orthogonal because we want z to be orthogonal to the whole surface, and that's going to be true for any x and y because we want z to be orthogonal to the whole surface, right? So people understand that? Yeah. Z is a vector here. Right, right. So right now we're just doing this special case, ax equal b. Okay?
So this definition hold only for ax equal to b?
That's right. So right now we're specializing to ax equal b, which is p of x is ax minus b, right? And so this is what it means for a vector z to be orthogonal to that set C. Okay? Yeah. Yeah. Right. So now what we're going to do is we're going to, that's right, z is a placeholder for the direction of the gradient. Did I see another question here? Yeah.
That's just a dot product you're doing, right?
That's right, just a dot product. Z transpose x minus y is z dot x minus y. So I could also write it as the inner product z x minus y, right, if I wanted to. It's the same thing. Okay, so here's an idea for how we might get such a z. Suppose we set z is equal to A transpose lambda. Why would we do that? Well, if we substitute that in, right, so z transpose x minus y is then lambda transpose A x minus y, right? Now, ax is supposed to be b, ay is also supposed to be b, so this is equal to lambda transpose b minus b, and that's equal to 0, right? And so if we do this, if we set z is equal to A transpose lambda, we've succeeded in getting a vector that's orthogonal to every vector that's within the space C that we're trying to do, right? Now, I'm not going to prove that this gets you every vector that's orthogonal, but in fact it does. And you can do that with an argument that's basically counting the dimension of the rank in the null space of A. Okay? So this then is what we're going to look for. We're going to look for we're going to look for the gradient being able to be expressed as A transpose lambda for some value of lambda, right? And then we'll get the gradient to be orthogonal to C the way we want it to. So that means what we've gotten is that we want g of x is equal to A transpose lambda, right? And if we have this, right, then if we have an x which satisfies the constraint p of x is equal to 0, and it also has g of x is equal to A transpose lambda for some lambda, then we've succeeded in finding an optimum, right? Does that make sense to everybody?
Z is a vector, right? It's a matrix. How does Z transpose?
Lambda is a vector as well. So in order to get A transpose lambda, lambda is going to be a vector, right? So lambda is in R to the K, right? So there's one, that's actually a very important point. There's going to be one Lagrange multiplier for every constraint, right? Every row of A. And we're going to adjust all of these Lagrange multipliers at once to try to match the gradient of x, right? So the dimension matches up, right? A is K by D, right? So A transpose is K by D, right? So this is a K vector over here, and sorry, let me write this out. So we have A should be shaped like this, right? with k rows and d columns, right? So A transpose is then going to be d by k. A transpose lambda, we can multiply the k vector lambda, get a d vector, which is the same dimension as gradient of x. Right? Yeah, so it always actually helps to count the dimensions of everything that I write on the board because A, it helps understand it, and B, you might catch a mistake where I skip a transpose or something like that. Okay, so now let's go back to the more general case, right? So if we define this matrix J, right, so this is going to be specifically J of x, which is the gradient of p with respect to x. And that's going to be, again, it'll be a matrix which is k rows and d columns, right? Then essentially the same condition is that, well, we still want p of x equal to 0, but we want then g of x, the gradient of x, is equal to j of x transpose lambda, right? And so if we had p equals ax minus b like on the last slide, then j would just equal a. Right? So this is the generalization of what I said on the last slide to curved constraint surfaces. Right? And in general, what we need is this Jacobian, right? This matrix of first derivatives, and that plays the same role as the constraint matrix A. All right. So these here, these are called the KKT conditions, right? They're also called the first order optimality conditions. So KKT stands for Karush, Kuhn, and Tucker, who are the guys who came up with it. But they're forever immortalized as KK and T. And these are a first order condition for optimality, right? So they only make sense if your functions are differentiable, and there are situations where they aren't enough to guarantee optimality. The simplest, of course, would be a local maximum or saddle point instead of a minimum, but there are fancier situations where you have to worry a little bit more. But if you're trying to find a constrained optimum, basically the first thing to do is to write the KKT conditions and see if you can solve those. Okay? So we're going to be doing KKT conditions again for more complicated things later in the lecture. So please ask me questions if you don't understand this.
So basically, you're turning to the problem above to this.
Right. So we're still in the problem min f of x, right, over all x, such that sorry, not ax equals b, but p of x is equal to 0. Right. The same problem from the previous slide.
Yeah, and turning to this like px equal to 0.
I'm sorry. What's the question?
So you turn into the minimization problem, the minimal fx.
Right. Right. So this is going to be, under many circumstances, exactly the same as this. Right? So these are the first order optimality conditions. If you have an x and a lambda that satisfy these, then the x is going to be a solution to this, or a local optimum, or a saddle point. Right?
In the constraints here.
Okay. So were there other questions? I saw more hands. Yeah.
So this is a mass-free observation.
That's right. That's right. There are ways that, so if you have this, then you must be at a local optimum, either a minimum, maximum, or saddle point of your function subject to the constraint. But there may be ways to get to an optimum without satisfying this condition. Or you might have a problem that doesn't have an optimum, right? Like, minimize 1 over x, right? And you're not going to be able to find the solution to that using the KKT conditions. Yeah?
Is there any connection between this KKT condition and the KKT condition in strong duality?
In strong duality?
Yeah.
Right. So is there a connection between this and the KKT condition in strong duality of linear or quadratic programs? And the answer is yes, and hopefully by the end of the class we'll make that connection precise. Yeah.
Lambda?
Nope, lambda can be any vector in Rk at the moment. We'll put conditions on lambda later. Yes?
Do we need to find lambda or just know that there is a lambda that exists?
Well, let's see. You need to, in order to prove that x is a norm, you just need to prove that such a lambda exists. But computationally, if you want to find x, it often involves finding lambda at the same time. Right? And so I'm actually on the next slide, second to next slide, going to give an algorithm for finding both x and lambda. All right, so we're happy with KKT. We like Mr. Karouche. So here's a picture of what's happening. So here's an optimization problem. Maximize C transpose X. So C is going to be a vector pointing just straight up in this case. Subject to, we lie on the surface of the sphere, x squared plus y squared plus z squared equals 1. That's this ball here. And A transpose X equal B. And so what's going to happen then is that A is going to be the normal of that plane, and B is going to be what slides it back and forth along the normal to make it be where it is, right? And so the feasible region is going to be this black curve here, where this blue plane intersects the surface of the sphere, right? And the constraint normals, right? So the normal to this constraint is just 2x, 2y, 2z. Right? We just take the gradient of the constraint, 2x, 2y, 2z, gradient of 1 is 0. And the gradient of this constraint, right, is just a, right? Gradient of b is 0. And so what we're trying to do then is at the optimum, we want to get that x squared plus y squared plus z squared equals 1 and A transpose x equals b. So we have to satisfy these constraints. And also, what we want is that the gradient of the objective, which is c, can be expressed as lambda 1 Lagrange multiplier times 2x, 2y, 2z, right, plus lambda 2 times the gradient of the second one, which is a, right? And so geometrically, if we are at the optimum, which is right here, right, so the 2x, 2y, 2z vector is pointing straight out of the sphere in this direction. A always points in that direction, and so they span right, that green plane, right? And so if we take that green plane, it actually contains the vector c, right? And so we've succeeded in finding an optimum. That make sense to people? I'm not sure whether silence is confusion or acceptance. Yeah. The functional form of C is a vector, right? So C is the vector 0, 0, 1, right? Just pointing straight up, right? And so C dot xyz just gives you z, and we're trying to maximize the z coordinate, just go up as far as possible, subject to these two constraints, right? And then the form of A, right? So this is C equals that, and then A is equal to, let's say the x coordinate is 1, 0, 0, right? So it's pointing off in the positive x direction. And then y, of course, is the axis going in and out of the figure. Okay? Yeah?
The green is perpendicular to the purple one?
Yes.
Is that just because of this particular problem?
Well, it has to contain the normal A of the purple one. That's not an accident. So the axes, I'll just put them up in the corner here, right? So z is pointing up, x is pointing to the right, and y is pointing into an out figure. Yeah.
Wouldn't A just be a scalar because x is a scalar in the second constraint?
Sorry. So I should have written this: A transpose x, y, z is equal to b. Thank you for catching that. I meant often we use x to mean a vector that collects all of our variables, and I was doing that without realizing that x also meant one of our variables. So I should have had a let statement around that one. Yeah.
What you want to illustrate in this slide is to say that that blue point, the optimal solution, is just a linear combination of the gradient of two.
Right. So at the blue point, the gradient of our objective C is a linear combination of the two constraint normals. Right? This is a graphical illustration of the KKT conditions, right? So it's saying there are two KKT conditions, right? One is that you have to be feasible, and that's these two things, right? So, and then this here is the first order optimality. Right? And so if you satisfy both of those, then you're a local minimum, maximum, or saddle point. Yeah.
So that is the bottom which point of the circle, right?
I'm sorry, say that again?
That condition can also satisfy the bottom which point of the
Right.
circle.
That's a good point. So here also satisfies the KKT conditions, and this is a pessimal solution, right? This is the worst possible solution. So if you solve this, then you have to check which one you get, right? Initialize a bunch of times and take the best one. Yeah.
If C was a function such that that plane did not intersect the circles, where would that be going?
Let's see.
There's no
So if C were a different vector, right? So C could be a vector pointing. It's very hard to draw, but OK, so we have our sphere like this, right? And C is currently a vector like that. If we just bend C like that, then we'll get a different optimal solution, right? And A is still pointing that way. So we'll take the plane spanned by A and C, right? And the gradient at that point, the normal to the sphere, will be in that plane again, right? So if you take if you take C and rotate it, it'll rotate the green plane, and then it'll intersect the blue plane and the circle at different points. Okay.
The bottom point as solution
Right. Right. So this is just like setting the gradient to 0, right? Setting the gradient to 0, we say that the gradient has to be in some subspace, right? And so if there were no constraints, the subspace would be just the single point, the origin, and setting it to be in the subspace would be same as setting the gradient to 0. So this is a relaxation or a generalization of the set gradient to 0. And just like set gradient to 0, it has the same flaw. If you just solve that condition, you might get a maximum or a saddle point instead of a minimum when you're looking for a minimum. And so you have to watch out for that.
Sorry, I
Yes.
still don't get, so in this formula, we don't constrain C.
C is a given. C is a constant, right? So you're given these two constraints, right? You're given A, B, and C, and you're given x squared plus y squared plus z squared equals 1. That's part of the definition of the optimization problem. And what you're maximizing over is just x, y, and z. Yeah.
The constraints were such that there was no. Is there a way for there to not be a solution? Like if
Yeah, so one easy way to keep there from being a solution would be to slide that blue plane until it didn't touch the sphere anymore, right? And then you wouldn't be able to satisfy the feasibility part of the KKT conditions.
So the lambda, how would that manifest?
Uh,
Lambda come out imaginary?
No, lambda, you just wouldn't be able to find an x that satisfied these two things, and so you'd be done, right? You'd be able to set, you might still be able to set a lambda to make this satisfied, but it wouldn't matter because you couldn't get an x, y, z that satisfied that one. Right? The other way, which is harder to show in this one, is you could make it so that there is a feasible solution, but there is no optimal solution. right? So an example of that is the one that I gave earlier. Minimize 1 over x subject to x bigger than 0, right? And so that is, it's bounded below, right? You can't get 1 over x below 0, but there's no optimal x, right? And so what that's going to manifest itself is that if you look at minimize x, right, so that's a vector pointing down, and if you look at the constraint normal, right, it's going to point anywhere from left to down, but it can't quite get to down and it can't quite get to perfect left. And so you're just never going to be able to find a point where you actually get equality in the first order optimality conditions. Yeah. What does what? The green surface is the span of this point, the normal to the x. It's the span of the constraint normals, right? So we have one constraint normal that doesn't change. A plane always has the same constraint normal. But if we look at different points on the sphere, we get different constraint normals. Here's the constraint normal at the optimum, and the span of this thing and A is that green plane. Okay. So, yeah.
So if there were, say, multiple solutions to the problem, for example, if you took the maximum of the absolute value instead of just the maximum,
right.
does that get you into problems with determining which one to use, or is that still just pick whichever one to get at?
Right. So actually, if you change this to absolute value, you would still get exactly these same two solutions to the KKT condition, but they would actually have the same value instead of different values, right? So what you do is you try and find all of them, and then you take the one that has the best objective value. Any more questions? So these are good, right? I want a geometric understanding of the Lagrange multipliers as well as just knowing KKT. Yeah?
Sorry, this is green surface. So that's the last constraint where you fixed x, y, and z to get optimal values.
That's right. That's right. So this constraint says that you have to be able to find lambda that puts you in the span, right? So this here, that's the green plane.
But then, like, really, you have another 2 dimensions to this.
Right. So you can mess with lambda 1 and lambda 2 as well as with x, y, and z. But if you're going to claim that a particular x, y, and z are optimal, then if you fix them, this is the green plane, and you have to have that c is somewhere in that green plane. All right. We're good? So now I promised you an algorithm, right? And Newton's method actually extends just fine to the case of trying to solve the KKT conditions, right? So if you remember, right, these are the KKT. They're just copied from before. And we already defined the gradient and the Jacobian, right? This is the gradient of the objective and the Jacobian of the constraints. Now we're going to take the derivative of the gradient, right? That gets us the Hessian, which I'll call h of x, right? Which is now a d by d matrix. And so I can make a Taylor approximation of p, right? So p of x is approximately equal to, let's say p of x plus delta x is approximately equal to p of x plus g of x transpose delta x, right? That's a first order Taylor approximation of p. I can also make a first order Taylor approximation of g, right? The gradient at x plus delta x is approximately equal to the gradient at x plus h of x times delta x, right? So these are just two first order Taylor approximations. And if I plug these into the KKT conditions, I get that p of x plus g of x transpose delta x. This was not g. You guys should have stopped me. This is j, right? The gradient of p was j. I defined here, right? So I was just checking dimensions. That's how I noticed that. So p of x, right? And so we'll get rid of this. This is p of x plus j of x transpose delta x, and that's supposed to equal 0, right? That's the first order approximation of the first KKT condition. And then g of x plus h of x times delta x should be equal to j of x transpose lambda for some lambda, right? And so I can collect those into a matrix, right? So it'll be this one here, right, has an h and a minus j transpose, h minus j transpose. This one has, that transpose shouldn't be there. Count my dimensions again, sorry about that. J, and then there's no component of lambda in this one, times x and lambda, right? And that is supposed to equal, here the constants are p of x and g of x. They're moved over to the other side, so they're negative, p of x and minus g of x, right? So by taking the KKT conditions, and just like we did in Newton's method before, we substitute a first order approximation for them. We get these equations here, which in matrix form are these guys, right? And this should be delta x, right? Okay. So what this is, right, we pick an x, we fix it, then h and j are constants, so are p and g, right? And then we solve for the delta x and lambda, and that tells us an update to make in the Newton step. And then we recompute this matrix and solve again, right? So just like in Newton's method, where we keep recomputing the gradient in Hessian at every new point, now we're also going to need to recompute the constraint Jacobian at every point. I believe I do. Thank you. Yeah, the g should be here. And here, we'll just minus g of x and minus p of x. I have it all written in my notes, so this is just a failure to copy correctly onto the slide, which is pretty bad. But yes, so do people understand now what the Newton method looks like with equality constraints? Okay, so another way to think about this is that this here, this g plus h of x delta x, this is our estimate of what the gradient is going to be after we make the update delta x, and we want that to be j transpose lambda, right? So we're basically taking delta x to be the update so that we can then make this gradient be in the span of our current approximation to j. Okay? So a useful special case is a quadratic, right? So if we're minimizing x transpose hx over 2 plus c transpose x subject to ax plus b equals 0, then the gradient is hx plus c. The Jacobian of the constraint is just a, right? And so the KKT conditions become h minus j transpose j0 times x lambda is equal to minus c and b, minus b, right? And this j, I wrote j, it's the same as a, so I'll just fill in a here, right? And so here, this matrix doesn't change. No matter where you put x, the gradient, the gradient is the same function of x, and the same linear function of x, and the Jacobian is always a. And so Newton on a quadratic subject to equality constraints converges in one step up to numerical precision, right? So you might need a couple of steps in order to deal with round-off error, but other than that, it's exact. Yeah? Right, so you could also write it as x plus delta x, right? So this is for our, this is the equation for our next step, right? So I could write, so if I write plus delta x and I consider x a constant, right, then I'll get minus hx over here and minus ax over there, right? So I could do it that way as well. I could write it either as what is the updated x, right, and call that x, or I could say I'm going to fix x and write it as x plus delta x for the update. So I'll take these off because I think it's less confusing without the delta x, but it's the same thing.
But on the previous slide, that was just delta x. That was x plus delta.
Right, so if I consider x to be a constant that's not 0, then this right-hand side won't be just c, it'll be hx plus minus hx plus c, right? So I'll write out the other form fully, right? So it's going to be h minus a transpose a 0 delta x lambda is equal to minus hx plus c and minus ax plus b, right? So yeah, you're right. There are two. If you set x to 0 in this one, then delta x here has the same role as x here, right? So this is for the first Newton step starting from the origin is maybe one good way to think about it, and this is for a general Newton step. And they're the same thing for a quadratic because Newton just takes you one step no matter where you start. Did I see another hand over here?
So how do you update according to this formula?
Right, so you update, this is the update formula here for x not equal to 0, right? And so you just plug in x to get the right-hand side, and then you solve for delta x. And you add delta x to x, and you're done.
So we can think about the formula without the delta x as a, well, you just write down the KKT condition and solve it.
Right, so this is essentially just writing down the KKT conditions, right? So if we have it in this form, this is exactly the KKT conditions from the previous slide, and it turns out to be a set of linear equations, and so we can just solve it, right? So for quadratics, Newton's method boils down to solve the KKT conditions.
But the form of it coincides with Newton's method.
Right. Right. This is why I'm pointing out both Newton's method and the KKT condition. Right. They both look identical for this case of quadratics, and so it's sort of two different sets of math that converge on the same answer. Yeah.
It'd be worth pointing out that shouldn't be surprising because what Newton's method does is make a local quadratic approximation and minimize that.
Right.
Quadratic or local quadratic optimization approximation is exactly what you're minimizing.
Right, right. And so Newton's method should get you to the optimum in one step. And since we derived what the optimum looked like as the KKT conditions, you would hope that they give you the same thing. If they didn't, they'd let you write a paper, I guess, right? All right, so KKT conditions. To give you an example where this sort of thing would come up in a machine learning problem, one common problem that you have to solve is given a robot that wanders around your environment and measures properties of landmarks. So let's say the distance of the robot to one of the landmarks or the bearing from the robot to one of the landmarks, right? What you'd like to do is solve for the robot positions here. So let's say that this is a vector x, which is in R2, the plane, and theta, which is an angle in minus pi, right? And so you want to solve for each of those, as well as the landmark positions, which are also in R2. And you're given odometry, like the distance the robot travels, what its turning rate is, as well as sensors like radar or time of flight, sonar, or vision sensors to give you measurements of the landmarks. And so you can set this up, right? This is a learning problem. We want to learn the map and the location of the robot from our observations. It's called simultaneous localization and mapping, right? Localization for the robot positions, map for the landmark positions. And the way we would do this, one common way, is called bundle adjustment, which is basically just you run Newton's method on your variables x, theta, and y, subject to constraints that you derive from your observations. So an example would be if you measured at time step t, the distance to landmark k was dtk, you might put in a constraint that said dtk squared is equal to the robot position xt minus the landmark position yk, right, norm squared, plus some error, right? And then we put min noise or noise squared into the objective, right? So, and you can see, like, you know, you're going to get a bunch of distance measurements. You'll also get constraints that the robot positions are consistent with your odometry, right? And you put all of these positions, all of these constraints into Newton's method, and you say minimize the size of the noise subject to those constraints, and then you get out something that looks like this. Okay? Yeah?
Now, the YK are fixed digits,
YK are unknown, right? So you start off not knowing the map. XT is also unknown. You also don't know and theta t, you also don't know the robot positions. And so the goal of this is to recover both the map and the robot positions at the same time. Okay, cool. So that's a good example. So now we're going to do Lagrange multipliers for inequalities. So in some sense, this is even more useful than it is for equalities. But before we get there, I want to do a brief review of constrained optimization formats, particularly linear and quadratic programming. Okay? So we'll go into that. So this should be review, but just to get it in front of everybody, right? We have n variables, a vector x, which has components x1 through xn. And we have ranges for these variables. And the ranges could be, right, so Li or Ui could be minus infinity or plus infinity, right? Meaning that it's unconstrained in that direction. So if you set them both to something infinite, you have a free variable, an unconstrained variable. If you set L to 0 and U to plus infinity, you have a positive variable. But in general, you can have any range on your variable. And then you have an objective, which is to min or max a linear function of the x's. Oh, OK. Right.
Oh,
I need that.
oh,
Sorry.
Sorry.
Are they? OK. So is to minimize or maximize a linear function, which is just sum over I of ci times xi for some constant ci, right? We can also write that as c transpose x. Optionally, plus a quadratic function, sum over ij, qij, xi, xj, right? So qij is also a constant. Actually, let's write that over 2 just to be consistent with what I'll do later, right? And so that is the same as saying x transpose qx over 2, right? Subject to m constraints, right? So for each one of these constraints, we'll have constants aij, right? One per a pair of a constraint in a variable, and sum of aij xi is equal to bj, so a constant bj, the right-hand side of each constraint. And this equality could be greater than or equal to or less than or equal to if we want to, right? And we'll write that as ax is equal to b, or is greater than or equal to, or is less than or equal to, right? And so here's an example. Maximize 2x plus 3y subject to x plus y is less than or equal to 4, 2x plus 5y less than or equal to 12, x plus 2y less than or equal to 5, and x and y are positive, right? So this format, everybody is familiar with it? Right? So just to sketch what that looks like, right? So here's the example from before. I just put it into MATLAB and had it sketch it. And so each constraint is a blue half space. Here is the feasible region. And it turns out that this right here is the optimum, right? And then this is C, the constraint vector, right? And then each one of these is going to wind up being a row of A. Right? Each one of the constraint normals will be a row of your constraint matrix. Okay, so everybody think that they could sketch an LP like this, given this, turn it into this, perhaps with the help of MATLAB? All right, and then the same thing for quadratic programs. They look exactly the same, except that the contours of the objective are ellipses, right? So a quadratic has, if you have a positive definite quadratic, it's going to have ellipses as its contours, and so the optimum then is going to be something like this here, right? It'll be in the middle of an edge at a point where the contour is tangent to one of these constraints. Okay? And contour tangent to one of the constraints is the condition that we're going to try and capture with the Lagrange multipliers. Yeah?
Is it still considered a quadratic program if the constraints are also quadratic?
No, that's called a quadratically constrained quadratic program if the constraints are quadratic. And it's a more general optimization problem, but it's one that you might run into. Okay. So I already basically put this on the slides before, but we're going to be using matrix notation, right? So we just collect all of the constraint normals into a matrix, collect all of the right-hand sides into a vector. This is the objective vector, right? And we write A times V is less than or equal to B component-wise. Okay? So Alex mentioned this last time. We can transform linear constraints, right? So we could get rid of every inequality other than variable bounds by saying something like x plus y plus a new slack variable s is less than or equal to 4, and s is greater than or equal to 0, right? So we can, sorry, not less than or equal to, but is equal to 4, right? And so we turn this less than or equal to constraint into an equal constraint by adding a non-negative variable into our formulation. We can also get rid of equalities. X plus 2y is less than or equal to 4 and is also greater than or equal to 4. These two constraints together are the same as this one, right? We can get rid of free variables, right? So here y is a positive variable, but x is free. So we can say that this becomes 2 x1 minus x2 plus y is less than or equal to 3, and x1 is greater than or equal to 0, x2 is greater than or equal to 0, right? So what we've done is we've split up this free variable into positive and negative parts and substituted that into this expression, and so we can get rid of free variables. We could also get rid of bounded variables by just turning that into constraints, right? X less than or equal to 2, sorry, x is less than or equal to 5, and x is greater than or equal to 2, right? So we can play around with the format of our problem and turn it into a linear program in a normal form. And there are two normal forms that we're interested in here. One is standard form, which has every variable non-negative and every constraint as an equality. So something like this, min C transpose x with ax equal to b and x greater than or equal to 0. Or inequality form, where you have only free variables, no variable bounds, and all constraints are inequalities, right? And we can use the tricks on the previous couple of slides to take any linear program and transform it into one of these forms, right? And it turns out that if you want to, you can put the constraint of full row rank on A, right? So in this one, A is going to be this shape, and in this one, A is going to be that shape, right? And you can put the constraint of full row rank or full column rank on A if you want to, and it's no reduction in generality. Okay, so that was the whirlwind review of linear and quadratic programs. We mentioned, I think, in different places all of this stuff before, but I wanted to make sure it was fresh in everybody's mind. So does anybody have any questions? Yeah?
Does this work with
Yeah, the same constraint, the same way you can transform linear constraints in linear programs, all of these work in quadratic programs too. And so you can get a standard form quadratic program, which is just a standard form LP, but you add a quadratic term to the objective, or an inequality form quadratic program, which is just an inequality form LP plus a quadratic term in the objective. Right? Right. Right. It would not work at quadratic constraints. That's one of the reasons why quadratically constrained quadratic programs are lumped in a different class than QPs. All right. Now back to Mr. Lagrange. So our goal over the next few slides is going to be to develop a Lagrange multiplier technique that works on linear and quadratic programs. And it's going to lead to a really important idea, which is duality. So what is duality? We're going to basically, a dual is something where you apply the transformation once and you get something different, and you apply it again and you get back to the same thing that you had, right? And so in particular, what we want is a duality for optimization problems. So we take one optimization problem and we transform it into an equivalent optimization problem that often looks very different. Right? And these are going to be called the primal and the dual programs. The original one's the primal, the transformed one is the dual. And then if we take the dual again, the dual of the dual will get us back to the primal. And why do we care about this? Well, the dual can be much easier to solve or much harder to solve than the primal. If it turns out to be easier, woohoo, you get to write a paper about it. And so this knowing how to do this duality transformation, what it's going to do is it's going to let you look at an optimization problem, and if you can't figure out how to solve that one, you get to transform it into a totally different looking one and try and solve that one instead. And sometimes you'll be able to do that. Okay? So there's a nice example of this, which is support vector machines, which we'll get to pretty soon. But there's plenty of other examples of this in machine learning. So duality is a pretty central idea. All right, so our goal, that was our goal. Let's start simple. So here's a really, really hard linear program, right? Like I stare at this and I'm having trouble figuring out how to solve it. Maybe not really, but let's pretend that it's really hard, right? So what I'd like to do is I'd like to make an approximate solution to it, right? So let's say that I pick x is 2 and y is 2. Right? So that's feasible, right? X plus y is 4. They're both bigger than 0. It has an objective value of 2 plus 2 is 4, right? How good is this solution, right? So you guys know, right? Because you can solve this thing in your head probably. But I can put sort of two bounds on the optimal value of this linear program, right? So if I just pick 2, 2, right, that leads to an objective value of 4. And so I know I have to be able to do at least as well as 4, right? The question is, how do I get a lower bound on the objective, right? If I could get a lower bound, I'd say, well, my lower bound is, let's say, 1, so I'm no worse than 4 times the optimal value. Okay? So how would I get a lower bound? Does anybody see a very easy way by looking at this thing to get a lower bound on the objective value? 2, right. Let's not always see the same hands, right? So here, right, one of the constraints happens to give you a lower bound on the objective value. So I know that this point is no worse than twice the optimal value. Okay? So you might say, didn't we just get ridiculously lucky that our objective appeared as a constraint in our problem? And yeah, so we did. So here's an example where the objective vector does not actually appear as a constraint in the linear program, right? But I'm going to take that same idea and see what we can do with it, right? So I can make more constraints, right? I can take A times that first constraint plus B times that second constraint plus C times that third constraint. And that's always and as long as A, B, and C are all greater than or equal to 0, I'm still going to get a valid constraint on the linear program, right? So let's do that. Let's take A equal 1 and C equal 2, right? So we get x plus y plus 2y, right? That's the left-hand side of this constraint, is greater than or equal to 2 plus twice 0 is 0, right? So here we have now x plus 3y is greater than or equal to 2. And voila, right? We found a constraint that gives us a lower bound on the objective. Okay? So that's a pretty cool trick. Did we get lucky twice in a row? No, actually. It turns out that this is perfectly general, right? So if we have any arbitrary objective subject to some constraints, we can take right, a plus b times that plus c times that for a, b, and c is greater than or equal to 0. And what we get is, well, on the left-hand side, we get a plus b times x, right? That's ax here, bx here, plus a plus c times y, right? And then the right-hand side is going to be greater than or equal to 2a plus 0b plus 0c, right? So this is sort of a generic form of the constraint that I can get by taking linear combinations of these guys, right? And so if I want this constraint, right, to be the same as this one, well, if I pick a plus b is equal to p, right, then the x terms will match up. And if I pick a plus c is equal to q, then the y terms will match up, right? And so I'll be able to say that px plus qy is greater than or equal to 2a, right? That's a q. All right? Yeah.
Solution is not unique, right?
Right. We can get many, many different bounds by choosing different values of a, b, and c. So the question was, the solution is not unique. And yes, that's true. The solution is not unique. Yeah. So LPs can't have greater thans in them. And so yes, the signs do wind up having to be the same. If you add together a positive multiple of a greater than or equal to with a positive multiple of a less than or equal to, you get nothing, right? On the other hand, if you add a positive multiple of a greater than or equal to constraint with a negative multiple of a less than or equal to constraint, then you're just fine, right?
What we need to make as long bound as large as possible.
I should pay you for asking that question. The question was, we want to make the lower bound as large as possible, right? So what that means then is we want to maximize this lower bound, maximize 2a, subject to the constraints we assumed, right? Which is a, b, and c all have to be greater than or equal to 0. A plus b equals p, and a plus c equals q, right? And this here is a suspicious-looking optimization problem, right? This is a linear program as well, and this is, in fact, the dual linear program, right? So we got arbitrary bounds by putting in different values of a and b that satisfied these constraints, right? The constraints were to make the x term and the y term on this left-hand side match up. Once we put those constraints in place and find the tightest possible lower bound, right, the largest value of 2a that lower bounds the objective, well, that's a linear program as well, and that's the dual linear program. Yeah?
Why don't you want to minimize 2a?
2a is a lower bound on your objective, and you want the tightest possible lower bound. So you want to maximize it instead of minimizing it, right? So the lower bound, the actual objective value is here. Our lower bound is here. We want to push the lower bound up until it hits the objective and can't go any farther. Yeah?
For the single but non-unique
Right. So if there are many A, B, and C that satisfy these constraints, there's a whole feasible region of this dual linear program. And that feasible region, it could be a line segment, a polyhedron, right? Anything that you can get by intersecting linear equality and inequality constraints.
but a single continuous.
Yeah, just like with an ordinary linear program, right? You can intersect subspaces and half spaces, and all of those are convex. right? And so intersection of convex sets is convex, and the feasible region of any linear program has to be a convex set. All right? So this is pretty cool. If you understand this, you're well above, 95% of optimization using people, right? This is a very useful trick. It's kind of mind-bending the first time you see it, right? This linear program doesn't look at all like this linear program, but they're absolutely equivalent, right? If you find they have exactly the same value, and it turns out that a lot of algorithms, when you solve the primal, you'll get a solution to the dual automatically. And similarly, if you solve the dual, you'll also get a solution to the primal automatically. Okay? So, any questions on duality or other mind-bending, mind-altering substances? Yeah?
Where do we know that it wouldn't be answer to the dual is the same as the prime?
I'm sorry?
How do we know that the answer to the dual is the same as the prime?
How do we know that the two problems are equivalent? The answer right now is that you just trust the professor. But if you're really curious, there's a very nice course, 10725, which is optimization. And it goes into duality in much more detail than we're going to have time here. Yeah?
What if A is larger than P or C is larger? A is larger than P.
What if A is larger than what?
P or Q.
Oh, right. So then you're never going to be able to find a feasible solution with A bigger than P, right? So that tells you something about the feasible region of the dual program. Yeah?
So does it mean you can't have for the original program, you can't have a target function, objective function where P and Q have different signs?
Right, so you'll never be able to get, so the optimal value of the primal program is going to be the same here as the optimal value of the dual program. And so if you find a feasible point, that gives you a lower bound on the value of the optimal solution to the dual and the primal, right? And so you're never going to be able to find a primal feasible solution whose objective is better than that.
I guess I mean if you're trying to minimize Px plus Qy and it's like P is positive and Q is negative, you're trying to minimize some difference between.
Right. So let's say P is +1, Q is -1, right? So you will be able to see then that Q is -1 here. You're never going to be able to satisfy this constraint, and your dual program is infeasible in this case.
Does that mean since
So if your primal program is unbounded, if you can keep pushing the value lower and lower without bound, then your dual program is going to be infeasible. Same thing with the dual program. If it's unbounded, you can keep pushing it higher and higher, then your primal program has got to be infeasible. So you're asking about a nice special case that's important, right? What if one or both of the primal or dual are infeasible? And you can come up with examples of those. The typical case is that both the primal and the dual are feasible, and if that is true, then their objective values are the same, and and one gives you a bound on the other.
but it's possible to have just one feasible and not the other.
It's possible to have just one feasible and not the other, and what that typically results from is that the primal program is unbounded and the dual is infeasible, or the dual is unbounded and the primal is infeasible. Yeah?
By convention, do we just call the primal function the minimization function, or is it just whichever?
By convention, primal is the one that you thought of first. So different researchers could call the same program primal, right? But yeah, I mean, often there's some obvious way to write down the constraint set and objective, and people will call that the primal, and then you take the dual to get the less obvious way to write it down. So typically the dual is the less obvious one, but obvious is in the eye of the beholder, and so people could disagree on which is which. Yeah?
Could you please explain a little bit more about recovering one solution to another?
Recovering, that is actually non-trivial to recover the primal solution from the dual solution. The best advice I can give you is use software that gives you both if you want both, right? Yeah, I don't think there's a fast answer I can give you on how to recover the primal from the dual. If there were only equality constraints, right, then you would go through and there'd be this linear equation for the KKT condition, and you just have some of the variables fixed in that, and then you'd solve it, right? We'll get to the KKT conditions under inequality here, and it will be an optimization problem still to recover one from the other. It might be an easier optimization problem. Did you have a?
For every bounded primal, does that always exist the dual?
Let's see. So if your linear program is feasible and bounded, then the dual will also be feasible and bounded. That's going to fail for more general types of optimization problems, but linear programs are nice that way. All right. Cool. So we're all good with duality. So I'm not going to do equality constraints separately, but you could imagine what you're going to wind up doing, right? You just add together A times this, plus B times that, plus C times that, plus D times that, right? And A, B, and C have to be bigger than or equal to 0, and D will be free, right? It can be either positive or negative. Okay? All right, and probably the last thing we'll have time to do today is duality for quadratic programs, right? So quadratic programs are just like linear programs. Here's only slightly harder. Here's a generic quadratic program, right? Minimize a quadratic function of x subject to linear inequality constraints. So we're going to get a vector of Lagrange multipliers lambda, right? And we're going to write down the generalization of what we wrote before, that lambda transpose, so lambda is going to be greater than or equal to 0, right? And lambda transpose times b minus ax, right? So every component of b minus ax has to be less than or equal to 0. Every component of lambda has to be greater than or equal to 0. So this whole thing, this is going to be a scalar that's less than or equal to 0. Right? So that's the generalization of what we did before by just writing separate Lagrange multipliers for each one of a list of constraints. So just like before, we're going to guess a constraint on our Lagrange multipliers, right? So before we guessed here, right, that this was the constraint on our Lagrange multipliers, right? And for a quadratic program, I'm just going to tell you what the right constraint is so that we don't have to go through the derivation. There is a derivation in the notes in the slide handout, if you're curious. But we just guess that A transpose lambda happens to be, that's a lambda, happens to be equal to C plus H times X. OK? And if you're curious why, again, check the notes. Then this here, right, that's less than or equal to 0. That's the same as saying lambda transpose B minus, so lambda transpose A, right, that's the transpose of this thing. So that's just going to be C plus HX transpose X. And that's going to be less than or equal to 0, right? I just substituted this guy and this guy together to get that thing. Okay? So now I'm just going to split this apart into two pieces, right? So I'm going to keep lambda transpose B on the left-hand side. I'm going to keep minus a half X transpose HX, right? That's half of this term on this side. And that's, I'm going to put the CX on this side, C transpose X. And then the other half I'm going to put up here, plus half X transpose HX, right? So everybody agree that that's valid, even if it's not clear why I did it?
Shouldn't that be H transpose?
H is symmetric. Right, all Hessians are symmetric, so I can skip transposes on H. That's a good question. Okay, and so this thing here, right, that's our objective. And here we have a lower bound, right? So that's one justification for making this assumption, is that it happens to lead to this. But there are better justifications, and again, I encourage you to check the slides. Okay, so now then the dual is going to be to maximize this lower bound, right? So max, so this is minimizing over x, right? We're going to max over lambda and also x, right? So x is going to be a variable in the dual. Lambda transpose b minus x transpose h x over 2, subject to the constraint that this is true, right? A transpose lambda is equal to c plus hx, right? And we also had to assume lambda greater than or equal to 0 to get this equation here. All right. So this here is the dual quadratic program. Okay. So if this here was the primal, then this here is going to be the dual. Okay. So again, there's one miraculous point, which is just guessing that this is the correct constraint to assume. But once you assume that, you very quickly get a lower bound on your objective, and finding the tightest possible lower bound subject to the constraints that you've assumed gives you the dual quadratic program. Okay. Does anybody have questions about that? Yeah.
So in the dual problem, shouldn't we remove x?
No. So x here is a dual variable as well as a primal variable, right? So what we should do maybe is rename x to z to make it clear that it's now a dual variable instead of a primal variable, right? So I'll put that here, right? Could rename x to something else like z for clarity. Right? And so a dual solution is going to be a lambda and a z, and a primal solution is going to be an x. Right? But there are z in the dual plays an exactly analogous role to x in the primal.
So that conjunct A transpose lambda equal to C plus HX.
Yeah.
It's true only for AX equal to B.
So this is an assumption that we're making on lambda and x, right? We have to choose x so that C plus hx is in the range of A transpose, and we have to choose lambda such that we get that equality, right?
From our previous slide, so that is going to that equal to minimize of the quadratic program with respect to constraint AX.
Right. So this is going to turn into, because we made this assumption, this is going to turn into a constraint of the dual, right? There's a constraint in the primal as well, ax greater than or equal to b, right? And since the dual and primal are related, the matrix A appears in both of those constraints, right? But this guy is a primal constraint, and this guy is going to wind up being a dual constraint. Yeah.
The constraint on lambda, isn't that just one of the KKT conditions?
Right, we're going to get to the KKT conditions soon, right? So this is, if you happen to know it as one of the KKT conditions, that's a good reason to guess that this might be the right constraint to put in to get the dual. But we're actually going to get to the KKT conditions probably at the beginning of next lecture. All right. Any more questions about this? So that seems like a good place to leave off, and we'll continue next Monday. Don't forget you have the project proposals are due Friday.